Also, there's nobody in Zoom as well. So. And also there's nobody in Zoom as well. We shouldn't waste time on it. Okay, good morning, and sorry for that interruption. I have to switch on this. Is it recording? Yes, everything is recording. So far what we learned is that the calculation of or analysis of line to ground faults using symmetrical components. I'll continue that part quickly today, extending it to line faults and line to ground faults, and then we'll go into a section on real relays and all. Okay, and I have uploaded an assignment. My original plan was I will upload it on Friday, but somehow I missed it, and I extend the submission deadline also until next week Monday. But yeah, so what I would expect from you is try to calculate those things, and then probably we can discuss. If you have any questions, we can discuss during the tutorial, right? So yeah, okay. So the second type of fault, as I've shown here, is line-to-line faults. In line-to-line faults, what happens is that two lines are short-circuited. It could be through some sort of impedance, but in this particular case, consider that the fault impedance is 0, so that we can do the first bit of proof, and then finally we will derive the similar equivalent circuit. Okay, so what happens is that when the two lines are short-circuited here, then one line is sound line, which means that its voltage is now still equal to its on voltage. But what is the current in line A now during a fault? 0. Why? We assume that load current is neglected. So that was one of the assumptions that in the fault analysis. The other condition is that current in line B is equal to current in line C in magnitude, but then they have 180 degrees phase shift because it is reversed. If you mark current from B to K here, it's going from K to C in the other line. So usually you mark all the currents in one direction. So it is basically the 180 degrees phase shift. And if we consider those factors, then you can write these relationships. The current in the phase A is 0, B is equal to minus IC, and VB and VC are equal. VB and VC are equal. Why? The impedance is now 0, ZF is 0. Therefore, those two are short-circuited. So if you consider these factors, and then if you write the equation to find, or the matrix to find the symmetrical components, right, VA0, VA1 and VA2, remember that these equations are written to the voltage at this point and the current considering at this point, right? It is the norm, so that always that we refer to the A phase, right? The fault happens between the B and C, we write it to the A phase. And then when you are doing some sort of analysis, if the fault is between A and B, you can write these equations to the phase C. If it is between A and C, you can write those equations to be, right? So it is because it's on the very symmetrical system, right? And by considering all these relationships here, then when you write the voltage equation, you can say that VB and VC are equal. Therefore, instead of VC, we replaced it with VP. So if you rewrite this, then simplify it, then you can say that VA1 and VA2 are equal. Here, VA or this A here, A is equal to 120. Okay, it is the lambda. Basically, can you remember the lambda? This is sorry, it's 100 and no, that's fine, correct. Right? If you go back and then read your notes, I mentioned that some people use alpha, some people use lambda, A, right? They are the same. Okay, now why these two are equal here? Because you can see that these two terms are equal, and then these two terms are interchanged here, right? So if you multiply A squared by VB plus A times VB, in the other one, A times VB plus A squared VB, they are the same. So therefore, VA1 and VA2 are equal. So which means that if you are looking at the fault between B and C, then positive sequence and the negative sequence voltages at A, they are equal. Looks like two parallel, they are like, let's say if you have two resistors connected in parallel, their voltage are equal, right? Let's say if the two resistors are connected in parallel, voltage across those two resistors are equal. So if the two voltages are equal, which means that it looks like those two circuits are in parallel. Now, let's look at the current part of it. The current, again, you can rewrite the same set of equations, but we know that IA is equal to 0, and then IC is equal to negative IP. So that is that is what I have replaced here in the equation. So if you resolve this one, then we can say IA0 is equal to 0. Why? Because you can see that IA0 is 0 plus IB minus ID, which is equal to 0. So what does that mean? There is no zero sequence current in the system, right? For a line-to-line fault. If the zero sequence current is not there, then what should be the zero sequence voltage at that point? To have a voltage, you need to have a current there, right? Across through and zero sequence impedance. But there is no zero sequence current. Therefore, there is no zero sequence voltage. And also that you can see that the magnitude of positive sequence current is equal to the negative of the magnitude of the, magnitudes are equal, but the direction is opposed. So if the I1 is going in one direction, IA2 is going in other direction. So you can have some sort of a parallel circuit where that the voltages are equal, but the currents are going in opposite directions. So how do we draw that sort of circuit? Like that. You can see that the fault current A1 is going in from left to right, A2, because this is the right hand part is the negative sequence circuit, this is the positive sequence circuit, they are connected in parallel, right? So they are connected in parallel. So VA1 and then VA2 is equal to, they are equal. And then the current A1 and A2 are equal but opposite in the directions. So this is the equivalent circuit for a line-to-line faults. So once you find positive sequence network, negative sequence network connected in parallel, then that will give you this circuit to find the corresponding values. So once you find these values, then yes, you need to go back and then find the fault current or B or C, because IB or IC or fault current, they are equal. So how do you find that? You have to apply. Again, we know that IB is equal to So IA plus lambda squared, lambda times IA1 plus lambda squared times IA2. So you have to use that equation. Okay? Clear? What happens then if you put an impedance here between the lines? So how do we replace it, change this? It's a very simple change. You introduce this one. If there is an impedance in between two lines, it is the same two circuits, but you need to put a impedance in between those two circuits. So that becomes the equivalent circuit for a line-to-line fault, right? So in the fault calculations, the tricky part is finding these corresponding impedances, not looking at these like the circuit we know now, right? If it is line to ground, you can put everything in series. Line to line, you put everything in parallel. If there is an impedance between them, then you put it in between the two parallel circuits, right? So this is the same exercise that we discussed. So I will leave it to my, the next class, right? I will show you the calculations. This is for you to use the same circuit that we discussed. Can you remember that in the last class? Probably I can show it to you. We have calculated the positive sequence network and the negative sequence network, and then give me 1 second. I think it should be in one of my papers. Fortunately, I'm missing. Oh yeah, this one. Can you remember this part of the calculations? Yeah, so for the positive sequence network, we have this one, right? Finally, we found the positive sequence network here. And then the negative sequence network, we found that the total impedance is this one, right? So for this specific fault, are we going to consider the zero sequence? No. Why? It is a line-to-line fault. In a line-to-line fault, it is only the positive sequence and negative sequence, right? So we don't need to derive this part, but we need to connect these two circuits in parallel. So we can connect this impedance here and then do the rest of the calculations, right? Try it out yourself and then we will discuss it in the next class, okay? So that is an exercise. Because we have already covered the hard part of it, it is just to combine two circuits. Okay, so I will go through one more example here because since, let's say, when you are looking at these sort of circuits, calculations might be a little bit different from the previous one where that you had Y-Y connections and then all neutral points were ground. So that the neutral, there is no difference between the zero sequence component network and the positive sequence. It was just a similar sort of negative sequence and zero sequence. They were quite similar, right? Positive sequence, you have the voltage source, right? But when you have these sort of circuits, now you can see the left-hand side is delta, right? If the delta is connected to 3 lines, can there be a zero sequence current flow in those 3 lines? What is the zero sequence? Zero sequence means current with the same phase. Let's say you have 3 lines, the same current are coming through those 2 lines. What happened at the end? Then there's no way to take it away from those 3 lines, because its addition of those 3 lines is equal to 3 times that current, and then there's no return path to carry it away, so that you can't apply the Kirchhoff current law there. It violates the KCL, right? If you have, say, 3 lines, IA, I will write the same magnitude of the current is going through, right? So let's say it's 0, because it is the 0 sequence current, and then this connect to some sort of a box here. Let's say right? Nothing comes out, only these 3 lines are connected to that box. Inside you can have Y or delta or whatever, right? There's no other wire coming out of it. So if you apply KCL to this box, what happens? There's a current going in and nothing comes out, which violates the KCL. So which means that if there is no return path, then the zero current sequence current cannot exist. So there is no way to have it. So that's why when you have these sort of delta connected systems, you have 3 wires, but there is no return wire there. So if the current comes in, and then there's no way to take it back, which means that zero sequence here, in this part, no zero sequence. What do you think about inside delta? Can there be zero sequence inside delta? What do you mean by zero sequence? The same current in all phases. Same current in all phases. Write it like this. Okay, I have a current IA0 here. Same IA0 is going through here. So, violating the conditions, now you don't need anything coming in from outside. This current is going through here. And then the same current is going through here. So, it means the zero sequence current can circulate inside the delta. It can circulate inside the delta. The other currents can come through here, whatever the current, and then those 3 will be balanced. Addition of those 3 will be equal to 0, right? But in addition to those, there can be a zero sequence current flow inside delta like that, because that doesn't violate the KCL. See, the current coming here is going through there, and then that current is going through here, and again going through here, right? So if you have a delta connected windings, zero sequence current exists inside that. It's circulating, but it's not coming out. So zero sequence current might produce zero sequence voltages, right? Because of this current, some voltages will be produced here, and you will see those effects in the magnetic fields. So which means that there will be some DC offsets, right? That sort of things. So it's existing, but you don't see it in the lines, right? So what is the impact of it for us, for a fault calculation? Since it's not going through this line, it looks like nothing is coming from here to the transformer. Zero sequence network is basically blocked here. Nothing is coming through this line. You can't, right? If something is not coming, which means it looks like very high impedance. If there is a very high impedance, then there is no current. What is the highest impedance that we can get? Infinite. How do you get infinite impedance? Circuit is open. So that's why for a zero sequence current, when we draw the circuit, you will see that there is a open part of the circuit. I will show it in the next part of the lecture. Okay. So number one for this question, you need to find the base basically per unit, because everything is given in different bases. Let's say, now the bases, like in this particular case, the impedances are given in percentage into one base, right? But we need to change this impedance value into the per unit quantities. Therefore, first you need to find the base. What are the base that we can select? Let's say in this particular case, see, this is not a good idea, but just for the teaching purposes, I changed the base to 100 MVA. Otherwise, when you are doing it in the, let's say, exam, you can go with the 75 MVA. That is much easier. Okay? And V base delta, 11.8, V base Y side is 66, depending on the transformer voltage ratios. Next, we will calculate the base quantities for the delta side. For the delta side, we know that I base is equal to S base divided by square root 3 V base delta. So that this 11.8 is the numbers and 4.89K. Next, Z base. Z base is V base squared divided by S base. 11.8 squared divided by S, we took it as 100 MVA, 1.39. Y side. Y side, we repeat the same, but Z base, you can calculate the value here. So now we know all base quantities for delta side and the Y side, right? The next step is that converting every parameter to corresponding per unit quantities. We have only the first is a generator one, because now since I took the 100 MVA voltage, then I have to change it to 75 to 100, right? This is the old and new, the voltages are the same, therefore that's cancelled out. So generator 1.233. Now same thing will be done for the negative sequence impedance, and then the same thing is done for the transformer, all three impedances. And then in this particular case, because usually delta to Y transformer, zero sequence impedance is probably from 80% to 100% of the positive sequence impedance, right? In this particular case, I have taken it for the, it's easier for doing less calculations, so I put it as the same as positive sequence impedance, right? So just to reduce the number of steps. So all these impedances are equal to the corresponding impedance per unit value for 100 MVA base. That's what is done here, right? 75 divided by 75 multiplied by 100. And then this is why I didn't consider any zero sequence impedance for generator. Any idea? Pardon? Yeah, see, delta, we don't know whether the generator is delta or Y. It's not given, right? But we know that after the delta, this part, there is no fault, the zero sequence current flow. So which means that we don't need any, zero sequence impedances of this guy. There's no current flow from there. I will show you the equivalent circuit diagram, then it will be more clear. Okay, so the next is calculating the Zn. Now Zn is connected to the Y side of the transformer. Therefore, you need to consider the Y side per unit quantities, base quantities. Okay. And then the other thing is that in the question, this is very important. In the question it says at the fault, just before the fault, voltage was 70 kV. Just before the fault, the voltage was 70 kV, which means that you need to convert it to that, basically the base that you are now using. So your base is 66 kV, right? So if you need to convert it to the correct per unit quantity. So that, can you remember in the positive sequence circuit, you have a voltage source, right? Positive sequence circuit, we have a voltage source. The value of that voltage source depends on this voltage. And that is the voltage just before the fault. That is the generator voltage just before the fault, right? So that's why we need to identify what. In most of the cases, it is 1 per unit. That's why that we put in most in 1 per unit, right? So I just wanted to show you that it is not the case always. It can be different. Okay. So once you find that, the next is defining the sequence networks, right? So now we have 3 sequence networks, and then we need to connect them in different ways depending on which type of fault that you are going to look at. So I have drawn this here. You can see that for the positive sequence network, always we need to have some sort of a reference for all these networks, right? So from the reference point, voltage source, and then the positive sequence impedances of the transformer, and then generator. Transformer and generator. See, from here to generator, the transformer impedance is there, and then generator impedance is there. You don't consider this one for the positive or negative impedance, the sequence networks, because there is no positive sequence or negative sequence current passing through the neutral. Now look at the negative sequence. Again, it is the transformer and the generator. Easy, right? It's the same as what we did before. Look at the zero sequence. That is the difference. See, the zero sequence current is now going through this part of the network. Y side, because from the fault, transformer goes to the transformer neutral, goes to the ground, and then coming back to the fault location. So there is a closed loop for zero sequence here, right? So how do we represent that? We need the transformer impedance, we need this impedance. So the transformer impedance is ZTO, and then the neutral impedance, as we took in the previous cases as well, it is 3 times the neutral impedance, right? Because the current through the neutral is 3 times the current in one phase, right? Because zero sequence current, addition of all 3 current is passing through the neutral. Therefore, we take 3 times the neutral impedance. So now you can see that from its reference, right, it's going through the Zn and then coming back and then coming through the transformer, going to the fault location. See, from the reference, neutral, like that. Now if you are looking at the other side of this side of the left hand side of the transformer, the delta side, the generator may have some impedance, we don't know, right? If it is delta, it's not, but if it is Y, then yes. So if you put that generator impedance, then that impedance is connected to here, but there is no impedance between the generator to the transformer. So that's why I kept it open here, right? In this path, there is no current flow. That is the current coming from generator, but there is no way to go. So that we can say that no, the current is not coming from the generator here. So that you keep it open. And then if this path is open, then we don't need the magnitude of this one. If it is open, means that you can just neglect this part. Okay, now once you have this, now the question says calculate for 3-phase, line to ground and line to line. 3-phase is easy. We don't consider positive or negative or zero sequence networks. It's only this, the one in red. That is the 3-phase fault, right? We have only a basically positive sequence network, right? Because all 3-phase currents and voltages are forming a 3-phase system. So it is easy to do the calculations. Once you find the I1, then you can find IA, which is 3 times the current that you found here. And then I think there is a mistake here. Sorry. Right? Because this is the addition of these 3 currents. Yes. And then it can't be the same as this. I will correct it. Pardon? Oh yeah, yeah, sorry. Yes. Right. Need a coffee. Got it? Yeah, I confused? It's only the positive sequence current, so that IA is always equal to the positive sequence current. Right? So these two are 0. Right? Because this is only this circuit. These, you don't need those circuits. Right? And then IA is addition of those 3, of course, which is equal to the same as. And then, if you want to find the real current, you need to multiply it by the base quantities. This is I base. Right? So that is what it is. It is easy. But then, line-to-line fault. In line-to-line fault, these 2 circuits are connected in parallel. You can see that when I connect it parallel, which means that the out, like let's say the fault point of this circuit, positive sequence circuit, is connected to the fault point of the negative sequence network. That's what I have done. See? So you can see that I1, which is the positive sequence current, is equal to the, if you go through this path, negative of I2. That is what we need. Right? That's what I said. In a line-to-line fault, positive sequence current is equal to the negative of the negative sequence current. See? Right? And then the voltage here is equal to the voltage here because they are parallel. So VA1 is equal to VA2. So you take these 2 circuits, and then once you find it, it's just simple resistive circuits, right? Voltage divided by the addition of all those impedances. See? That part is easy. So the fault calculations, the tricky bit is forming these networks. Other part is straightforward. If it is line to ground, all 3 circuits are in series. When you are connecting them in series, you can clearly see that this bit is not required. There is no current flow in that path. Right? So the most important part is that for these transformers having very different configurations, it could be delta to delta, Y to Y, delta Y, one is grounded, one is ungrounded. You can have heaps of different zero sequence circuits. Did you have time to go through your notes in the learning resources? Probably there is one document which I put. What are the potential circuits, or what are the circuits for these different arrangements? I will, if you want, I can. I really don't want to go with some because I don't know whether I can come back. Okay, so please look at the learning resources, and there is one file with for each and every different combinations of transformer windings. There is a separate circuit. Okay, so that gives you some understanding of course, if I am going with this, I have to use this. If you have any questions related to those circuits, please come and talk to me in the next class. The next is line to ground fault. I am not going to derive everything, right? It is now we have done it for line to line and line to ground. So I will just show you the equivalent circuit. So the equivalent circuit is the same as before. You can see that positive and negative sequence are now equal. Not only that, you can combine or
or you can put another branch in parallel, which is the zero sequence branch, right? And then the zero sequence impedance, and then there is a fault impedance as well. If the fault impedance is not there, all three voltages like A1, A2 and A0, that is the positive sequence voltage, negative sequence voltage and zero sequence voltages are equal. If the fault is line to ground. Okay, so you can prove it the same way that I did. Put the conditions, like as an example, in this case you can say that IA is equal to 0 and then VB, VC is equal to 0, right? Because VB and VC, they are short circuited and grounded, right? So once you put all those conditions and then rewrite those matrices, you will end up with this. Okay, so what is it? Three sequence voltages are equal. But if you have a fault impedance, then 3 times the fault impedance is in series with the zero sequence network. Why? Because always remember that zero sequence is only going through the ground path. Therefore, always zero sequence is in series with 3 times the ground impedance. That's what you need to remember. Okay? So, yeah, so that's the other equivalent circuit. And then another example, the same as before. You can see, yeah.
What is sub-transient impedance?
Yeah. So can you remember that in the first one that I mentioned about for the generators? When the generator is under fault, you will have 3 zones. One is called subtransient, the other one is transient, the other one is a steady state. So what happens is that when the generator's armature reaction and then the magnetic circuit interaction and then damper winding, all those things are interacting in a way that it reduces the total reactance of the generator for a very short time period, very, very short. So that during that period, there will be a very large current flow or a current spike. After a couple of cycles, then this effect reduces, and then that effect, once it is reduced, means that the impedance slightly increased. So the impedance is increased now, so the current drops. And then when it goes further down, then there is a sort of always, if you look at this mathematical expression of this current flow, then you will see that during a fault, there is a DC component. That DC component is exponentially reducing. So which means that after some time you come to the steady state. So that usually in a fault you will have 3 different zones: subtransient, transient and steady state. So that's why that, but in the fault calculations we are looking at the worst case. Worst case comes when the impedance is highest or lowest? Lowest. What is the lowest impedance? Subtransient. So that's why that we do the calculations with subtransients, so that your system is safe, right? So that's yeah. Okay, so this is another question. You can see that these two are connected in YY, and then they are grounded as well. But the fault is in the delta side. Fault is in the delta side. Is there any fault current or zero sequence current coming through all the way from here to here? Can it happen?
Zero.
No. Why? This delta will block it. There is no zero sequence current flow between this transformer and this fault location. Why? The transformer is delta. But if there is a fault here, definitely there will be a zero sequence current in this network. Why? Because this network has Y network, both of them are Y networks with grounded neutral. So if there is a fault somewhere here, then the zero sequence current exists. But if the fault is here, then if the fault is here, there is no zero sequence current going from this delta to that. Right? If there is delta or Y without neutron, remember, it's not only delta. Y without neutron, you can't have zero sequence. Right? Always a ground connection should be there. So when you draw the equivalent circuit for this, so the first step is, again, I'm not going into the base calculations and then finding the corresponding impedances. That is the common part of it. All impedances, convert them. Now this is the interesting bit. These two are very, it's the same, right? You can put all impedances and then find where the fault is. So now you have two circuits in parallel, this part and then this part, right? Because from the fault location you will have two generators. If you have three generators, all three generators are in parallel from this location, right? So if you are looking at here, one generator is this side, the other one is this side. So you can use Thevenin equivalent circuit to find out what is the equal voltage, which is of course which will be 1.05, right, always, because the E voltage, supply voltage at this point, if you open it, then that will be this voltage, right? And then impedances, this set of impedance and this impedance is in parallel. You can see that here. Okay, that is the simplification of this positive sequence network. Now, if you are looking at negative sequence, again, from this point to here, and then from this point to here, you have two separate networks, right? Right-hand side, if you go back, it is not clear. Right-hand side is the connection from this point to the generator to the ground. Left-hand side of that network is from this fault location to the transformer, through the line to this transformer to the generator. So from the left, in the left-hand side, you will have 1, 2, 3, 4 impedances, right? So that's what you can see here. 1, 2, 3, 4 impedances, right? Same for this one. Now let's look at the zero sequence, which is the more interesting one, right? See, 0, the voltage, the fault occurred here. This is the generator impedance, 3 times of it, and then generator zero sequence current, right? Going to the fault. Now it is open towards the transformer. Why? Transformer is delta. But inside the transformer, the other side of the transformer is Y connected with ground. So that's why these two exist. But there is no current, there is no let's say link between this part and this part, right? If this current comes here and then it goes through this part, right? This part will not have any impact on the current zero sequence current flow. And then you will see that generator side is also, generator has some zero sequence impedance, and then this part is open. So it doesn't have any impact at all. So we can just neglect this part. Okay? So that's why it ended up with this simple one, addition of these two. See, J.25. Once you have these three, then it is easy. Line to ground, connect them in series, line to line, connect them in parallel, and if it is only 3-phase, then only consider the positive sequence. Okay, now I found that problem with the connector here. Okay, so that is what it is here, line to ground fault. You can see that everything is connected in parallel, right? See? And then zero sequence is also connected in parallel. Straightforward. Find the values, and then once you find I1, I2, then I0, then after that it is quite easy, the other part, right? IA is this much, IB is this much, IC is this much. Yeah? Got it? Clear? Right? So this sequence calculation in sequence component is important, but also remember that the part missing here is that we didn't calculate the fault current, right? If you want to calculate the fault current, then you have to look at IB or IC, remember, because the fault occurred between B and C, not IA. IA will be 0 always. If you calculate this, if you add them, right, 1, 2, 3, then it will be 0, right? Yeah, see, like that. And then you can see that IB and IC 180 degrees out of phase, because they are, the fault is in between. And then not always, because if it is going into the ground, sometimes it's not, right? Two currents connected and then going into the ground, then it's slightly different. If it is line to line fault, then they are equal, right? So try these calculations, just go through them, and then what I would expect from you is that you will try to do it by yourself and then compare these answers, right? So that helps you to understand it always it's good to follow or repeat those calculations and then try to see whether you understood the concept. Yeah, so this is for the next week class, the Friday class. I will continue this question. It is the same as the previous one, so I will finish that part here, so that, which means that you can complete that assessment, right? It is based on line to ground fault, line to line fault, that's all, right? So that if you have any questions related to those, you can ask me, or you can post those questions in the discussion forum. Now I want to go into the real protection side of the course. Good. So if you are looking at protection, erase this. Isn't it too high for you guys? No? No? Okay. Yeah. The next part of the course is learning about the relays, right? So first I thought that it's better to understand what is a relay, and then what is what is a protective relay, right? Relays used in the protection systems, and then how you define them, and then what is the difference between relay and a fuse. Someone could think about, is a relay fuse? Is a fuse a relay, right? These sort of things. And then there are basic operation principles. And also that what are we expecting from a protection system? Like as an example, reliability, sensitivity, and those sort of parameters. Okay. So that whenever you come up with a design, or whenever you come up with a relay design system, it doesn't matter whether it is a, let's say, voltage, over voltage relay, over current relay, or whatever different types, these concepts are valid. So first of all, the primary purpose of the protection equipment is to, you can say that, maintain a high level of continuity of service, because you want to maintain the continuity of the service even though, or under defective conditions in the system. It could be natural or sort of physical accidents in the system, but you want to have some sort of a maintained high level of continuity of the supply, right? It could be some natural disaster, some sort of human intervention or whatever, sometimes the system could lead into a defective situations, but still you want to maintain that, the continuity of the supply. So therefore the relay involves with defective systems. If the system is not defective, there is no, the relay is not important, right? And then the other thing is that not only defective, sometimes the system is sort of behaving in abnormal ways. Like sometimes it's not defective, but say 100% defective, but sometimes sort of voltage level suddenly, okay, in a transformer, tap setting is now due to some reasons like let's say solar feeding or whatever, now the voltage level goes up a little bit, right? So it's abnormal conditions. Or sometimes it could be very dangerous conditions as well, right? So like as an example, if the voltage level goes beyond a certain limit, that could damage instruments connected to the system. So when you are looking at the relays, then the relay operation comes when the system is defective or it is dangerous or it is abnormal situation. So based on all these conditions, IEEE has defined it in this way, right? It is function is to detect these defective lines, apparatus or the power system units of an abnormal or dangerous nature, right? So that defect could be caused by these abnormal conditions, right? So that that is the basic definition for a relay coming from IEEE. But it's if you are looking at from the physical point of view, it is a logical element, right? It's a logical element. It's takes some logical actions based on some inputs. What are the inputs? Voltage and current, right? That is the main input for a relay. So that voltage and current inputs, you take some sort of the logical actions to okay, first it detects the defective conditions and then take appropriate actions to minimize the impact of that defect, right? So that is the last part of it. It initiate appropriate control circuit reactions. So that every relay does the same thing. Now the next question is this. If you think about a fuse, is it doing all those things or not?
It's doing voltage.
Pardon?
It's not checking voltage.
Yeah.
It's doing current.
Current. But say, is it initiating appropriate control circuit reactions?
Well, itself is the actual control.
Yeah. The control action initiate, but it's itself,
Yeah.
right?
Itself.
So it's like this, right? It's a protective device. Oh, it's only for overcurrent. Relay is not only for overcurrent, right? Relay can be anything, right? Any defect. So with a circuitry opening fuse, it has a fusible part, and then as we know that it is heated and served by passage of the overcurrent. So it is not 100% a relay, but it has some features of a relay. Put it in that way, right? And then I'm not covering quite a lot about the fuses, but fuse plays a big role in the network as well. Like if you go into distribution systems, transformers, they have fuses. Because the relays are expensive. You can't put relays each and every location in the network. Right? It's good, but you can't. And then also that relay, you need that appropriate control circuit, which means a circuit breaker. So you can't put breakers everywhere in the system. Nowadays they do it as, probably that's one of the, I will try to see whether that person is available to come and give you a talk, but have you heard about Noja Power? Right? So they produce these what you call reclosures. Right? So instead of fuses, what it can do is that it's the same as circuit breaker, but it can, when it detects something, it has some sort of a, say, these sort of it's an intelligent device, so that it can measure the current, voltage, and then if there is something in front of it, some issue, it can quickly open the network. So not the full feeder is disconnected now. Section of the feeder will be disconnected because you install it in parts of the network line. Like, feeder, let's say 100 kilometers, you can put it in every 25 or 50 kilometers depending on the number of customers, right? So it's up to, the design engineers where to put those things. So those sort of devices are there. They are more powerful than fuses, right? So fuse is, of course, still useful in the, especially in the distribution transformer levels. Okay, when we are learning about the relays, there was a big transition actually. It was initially electromechanical, then it was electronic type of relays, right? And then more towards the those electronic ones then became numerical relays, where that it became sort of a computer. So the relays, what you are going to use in the lab, they are basically a computer, right? So in a computer, you feed the voltage and current, what you measure, and then the computer will analyze them and then send the signals out to the circuit breakers. The difference is that it is, even though it is a computer, it's more sort of focused on protection systems, so that it is more reliable, and also that it has more communication protocols or channels or whatever different ways to communicate with other relays or other devices or human machine interfaces, a lot of different ways that it can program it. So those are the modern microprocessor based relays, right? They are advanced, but in this, like, since they started with these electromechanical relays, concept is still the same, right? So you are doing the same thing, but with some numerical calculations. Earlier in these mechanical relays, how did you identify whether you need to take an action or not? Is it based on what? Based on some mechanical movements, right? So as an example, if the current is high, exceeding certain limit, then a disk starts to rotate. How do you control those rotation? You can control by changing the, let's say, spring constant, because you have a spring, right? Or you can, the distance of the rotation you can control by putting some spindle at one location, and then it won't rotate more than that, something like that, right? So you can have a lot of mechanical arrangements to operate this, but all those things are not there in the digital, right? You can say that the speed of, let's say, when you detect this much of current, wait 0.2 seconds. You can instruct the processor, right? So those are the differences between these two, right? The concept wise, they are the same. And then type of faults cleared by this, it's not only these things. There are heaps of different, like frequency, it could be not over voltage or under voltages. Say it can be frequency, it can be temperature sometimes, right? If you are looking at the transformers, then pressure, right? So there are heaps of different faults that can be cleared by the relays. One of the important things for these relays is that, like, let's say if you expect a fault in the system, right? let's say there is a certain fault occurred, do you want to detect it within a very short time, or do you want to wait for a longer period? As quick as possible. You want to detect it, right? Therefore, the relays doesn't have big time window to operate. They have to take the decisions very quickly. Why? What are the issues with, if you take some decisions quickly, what are the issues associated with that? Of course, that you need to take it quickly, but what are the issues that could arise from that sort of action? Say, think about yourself, right? I'm sitting for an exam. I want to say, this is the typical issue with the exams, right? Exams are not the best way to assess someone's knowledge, right? That's what people say, even though we are doing it, right? Because that is the cheapest or available mechanism, but it's not the best. What is the reason? You have, now same as relay, you have limited time, right? I know there is a person that who is who had that issue within the exam, right? So think about that, right? When you come out of the exam, you know that I did something wrong, but you couldn't do it within that time frame, right? So why? Because you make mistakes when you do things very quickly. Relays, it will be the same, right? So the problem with time frame is that it can do a lot of things quickly, but when you are trying to do things quickly, then that can lead to sort of a erroneous decisions, right? So that you need to have some sort of a balance between accuracy and the speed. So those two are sort of contradicting things, right? You can't have very high accuracy and then very fast operation. You have to have a balanced. So if you are looking at these relays, then you can also change the operating times within some settings. Like same relay can operate, let's say, if the overcurrent is, let's say, 50 amp is defined as overcurrent, the same relay can operate in 1 second and 2 seconds. You can set it, right? So those are the time settings of these sort of relays. But some relays are called as instantaneous relays. Do you think that instantaneous relays means that they operate instantaneously? No, no way, right? So there is a small time delay, but that time delay is considered as instantaneous because you are not forcefully delaying it. The relay has its own delay, but you are not forcefully delaying it. So that typically, as I mentioned here, instantaneous relays can be from 10 milliseconds or always less than 50. Right? 50 milliseconds is still too long. Why? How many cycles? 50 milliseconds. For us, not
2 and a bit.
2 and a bit, right? 2.5, right? Sometimes 2.5 might be too long, right? So 10 milliseconds is okay because it is half a cycle. But imagine without going into a full cycle, if you are going to detect it, which means could be you are in trouble as well, because probably it was a sudden something spike, right? And then you are not going into this fault situation if you are, say, let's say if you allowed it to go further. So these sort of things need to be considered when you are working with the relays. So when you are looking at these protection systems, one of the important things that you need to understand is that the protection relays cannot foresee the event and protect the device. You can't do that, right? Because protection, to identify whether there is a protection, any sort of situation, the voltage and current has to change. So that before that event, you can't, of course you can identify, let's say if that before the event, if there is any sort of special thing happens in the network, yes, you can identify. But if, let's say, falling a tree branch on a line, right? Of course, if you know the wind and then if you know the tree profile and everything, probably you can predict something. But by looking at the voltage and current, it's hard because we don't know whether the tree is going to fall off on the power lines. So it's unknown. So that is just like always they cannot foresee them, but they can identify during the fault. So what they can do is that they can minimize the impact of that fault on the equipment or line or system. When you are doing this, or when you are looking at the relays, you have to look at 5 basic aspects, right? So when you are, because now you can't prevent it, so now the relay is going to minimize the damage. So when you design the relay, you have to look at these 5 aspects. I will go through those aspects: reliability, selectivity, speed of operation, simplicity and economy. Those are the main 5 facts. But I will go through them one by one, what they are. So reliability is that we know that how reliable it is, right? Whether it is operating properly to identify a fault. But when you are looking at the reliability, there are 2 aspects called dependability and security. They are sort of like if you are trying to increase the dependability, then the security goes down, that sort of thing. They are not like you can't increase both of them at the same time, right? So what they are, so that you have to come up with some sort of a high reliable system with a very good dependability and very good security, not the 100% of both. So what is dependability? The relay is said to be dependable if it trips only when it is expected to trip. When it is tripped, right? When it is expected to trip, right? This is slightly confusing, these 2 terms. So after I do this after finish the lecture, go back and then read those sentences again and again to get it, right? It's quite similar, right? It's so remember that the dependability is that if it trips only when it is expected to trip, right? But there are situations where it is tripped when it is not expected to trip. So we want to reduce those situations, right? So it's the degree of certainty that relay or relay system will operate correctly. Right? Because the definition says that it trips only when it is expected to trip. Now, how do we measure it? That is the next question. So what they do, the dependability is the number of correct trips, that how many times that correctly tripped for a number of desired trips. Like as an example, you wanted to have, there are 5 cases where that we want to trip, but the relay tripped only 4 cases, in 4 cases. So that 4 divided by 5. And then this number has to be less than 1, right? Because correct trips should be less than the desired or equal to desired number of trips. If it is more than, like let's say if you had more than the, let's say that number of trips, which means that they are not correct ones. Some of them are wrong ones, right? And then when you go to the second term, which is the security, we say that relay is said to be secure if it does not trip when it is not expected to trip, right? That's why I said that. Sometimes you feel this one and this one quite similar, right? See, it does not trip when it is not expected to trip. Which means that sometimes when it is not expected to trip, it will trip, which is an issue with the security. So how do you find that? Number of correct trips, again the same as here, number of correct trips divide by the total number of trips, right? So which means that if you have 50 trips and then 49 is only the correct ones, then there was a one which was a wrong trip, right? It doesn't mean that 50 is the number of desired trips, because one could be undesired trip as well, right? So it's so what happens is that when you are trying to increase the security, usually it tends to decrease the dependability, because if you increase the security, then that reduces the total number of trips. If you try to increase the security, which means the total number of trips will be reduced, right? So that could lead to decrease the total number of correct trips. So that's what happens if you try to increase the security of a system, then which means security of a system increase means you try to reduce those number of total trips, right? Unless assuming that like as an example, can you remember that in South Australia, if you look at that document AMO has produced, there was a problem with the settings of this, right? Probably it is less secure, could be, right? And then because it has, like if you reduce the security, increase the security there, then you could stop certain trips. But then problem is that the dependability issue is there, right? So that is why that production engineer has a big role here, right? Identifying what is the balance between these, right? There's no specific way or any definitions, but you have to find the best balance. So typically relays have more than 99% of the reliability. These are two examples to give you dependability and security. Here dependability is, you can see that a fault occurred in the line 1. Of course this relay operated and then circuit breaker opens, but this relay didn't work, right? So the dependability means that when it has to trip, it should be tripped, right? Now this guy didn't operate properly, but then you can see that the other guys, they now detect this fault, right? Let's say that these guys detected the fault here, therefore they operated. But when they operate all these breakers, like this one, and then this one, because it doesn't have any coordination between this breaker and then this relay, right? So what happens is that there was a fault here detected by this one, and then this part is disconnected, but this relay didn't work, therefore you can see that the other relays operated. So now you can see that because of this situation, number of lines disconnected, another generator disconnected. See, this relay didn't act the way that it has to, right? And then because of that, these relays, now you can see they act the way they have to, because they have to look after, they are the backup relays, right? And then because of this incident, the reliability went up. The next one is, say, for the same fault, now what happens? Before this guy is detecting, this guy operated, right? So it's called overtrip, some sort of a security type of failure, right? So now what happens? This guy detected it early, This guy also detected it, but before him he detected it, right? And then still, in this case, two lines, like this line is disconnected. It's not good for the reliability, but then better than the previous case. So case by case, you can identify what are the impacts of, because once you set these things, right, using PSCAT, let's say, you can simulate and then see how these things will be performed for different type of faults. Only issue is that you can't simulate every kind of faults that could happen in the system. Why? We have to tell the software that this is the fault, but we don't know what sort of fault can happen, right? You can say, you can assume certain numbers, but not 100% that you can think and then create a fault, right? If you know the type of fault, yes, then you can identify how the system behaves. So these sort of things can be done, and then one could improve the reliability. This one, the selectivity. The selectivity is also very important because the selectivity is that the ability of the relay for discriminating the different faults in the system. Like, let's say whether fault happens here or another location, or whether the relay should know or identify the difference between these two. So that is called the selectivity. And that requires to, let's say sometimes that we will learn something called relay coordination, which means the relays have to coordinate each other and take actions. So that for that purpose, the selectivity is quite important. And as an example in here, in this case, right, if you look at the, let's say, the protection zone here shown in, what is that color, blue color, that is called the protection of B2. The B2 relay is, or the relay connected to the breaker B2 is covered by this area. But then if this part fails, this guy is looking after this red area. But remember that this guy shouldn't operate before B2. So that is some sort of the selectivity is there. Their communication, coordination between those two relays is also important. The other one is the speed, right? The speed is quite important, but it is not only the speed of the relay. Remember, always breakers are there, communication channels are there, right? You have to add all those sort of time delays, right? Errors associated with the relays as well as breakers, right? It's like if you say that this breaker can operate in 150 milliseconds or something, there can be a plus or minus time associated with that. So that you need to, when you are working with the operating time, you need to find out what are the fastest and slowest operating times. And then you have to design based on those times for the worst case scenarios. And also, the relay speed is very, very important. Have you heard about something called stability of networks? Network stability, small signal and things like that. It's not, I'm not sure whether that is a part of this any other courses. I think there is a one called Mithulan is running. What is that? Market. I think it's market and security, right? So have you? You haven't done it, right? No. That's another elective. I think you're allowed to sit as well, right? I'm not sure whether you have, like, they are postgraduate, yes, but I'm not sure. I think you can sit, right? They're not restricted for undergrad. Like, I think transformer technology design and operation course. There's another course, postgrad. 7051. So in those sort of scenarios, then for sensitive networks, that maintaining stability is quite important, right? If you go away from those stable conditions, if the system goes to unstable conditions, then the whole system will collapse, right? So sometimes it is better to isolate a certain part of the network rather than losing the whole network. So that's speed is quite important here. What is simplicity then? Because simplicity is that you have to make it simple as possible. Reduce the number of components associated with the protection system. Why? When you introduce one component extra, that component will introduce, like if that component could fail, that component could introduce some delays, right? A lot of things. So it's better to have the system with minimum number of components, right? Economical is that always, say as an example, that you don't want to protect a system, say for, let's say, unexpected situations, right? Assuming that there will be a 10,000 kiloamp of current going through this system during this fault, like which will never happen, and then you try to design your wires and everything for that sort of thing. No, right? Because that is not economical. And then always, like let's say, we cannot avoid, or we cannot say that 100% my system is reliable, right? If you design it for 100%, then it is not economical. Like say, instead of transmission wires, that you can put underground cables everywhere then. That will increase the reliability quite a lot, but which is not practical, right? The cost comes into the picture. So when you are working with the protection, what you are doing is that maximum protection for minimum cost. So you have to identify what is the balance, like how many customers will lose the power and things like that. The cost, it should be evaluated against not only that I said that cost of the equipment to be protected, not only that should be evaluated against the cost of the loss. Like it could be even sometimes that you will have to pay some sort of a, what do you call this, there are say certain charges imposed on you if certain number of customers lose the power for certain time period, right? And then probably compensation payments, or probably government will charge certain, and then a lot of things like that, right? So you need to think about, that's why this thing came up, about when did the Noja power start? Probably somewhere in 2000s, right? Their solution is, say instead of you're losing 100,000 customers, let's say I come up with a proposal saying that I can reduce it to 25,000. By which way? I will segment the lines so that when there's a fault at the far end, still the customers in the initial part is getting power. So that was their proposal, and then it was very attractive everywhere in the world because the supplier has to pay certain damage fees for the customers, and then the government if there is a too long power losses, right? When you have that sort of regulations, the new technology is coming into the market, right? If you don't, let's say there's no such regulation, right? Nobody will put those things in the system, right? No, I don't care. I will reduce the number, I will try my best, but I don't have any issues with losing customers, right? So that's why that regulatory is sometimes important. And the other things, like there are a lot of other factors affecting the protection system, right? Personality is that, say, like as an example, if you go to PowerLink and then if you go to Transgrid, their policies or the way of looking at setting the protection systems is different. Like Every utility is different. They have their own way of developing because of the working, the experience and then their personality and all those things, right? And also that you need to look at the location and availability of isolating devices. Like as an example, whether you have these intermediate circuit breakers or or probably, let's say, if you are supplying to a hospital, right, you don't want to lose the power there, right? So then the settings might be different. And then what sort of indicators are there to identify the fault? It could be not only these, like there could be temperature, pressure, not only voltage and currents, right? Other measurements, like as an example, transformer, that you will have pressure measurements. You can have temperature measurements, right? When you are dealing with the generators, probably temperature measurement is quite important to identify whether there are any significant, let's say, zero sequence current flowing through the generator windings, things like that, right? So then heaps of different measurements are available. So that those indicators affect the protection system. If you have more and more indicators, then it's easy. We will learn many different type of relays, we will learn only about the protective relays. There are different type of relays here, right? It's not only for protection. Relay is for many different purposes, regulatory purposes, monitoring. There are auxiliary relays, right? So there are heaps of different purposes, right? Don't think that it is only associated with protection. And then also, based on the zones that we classify there. Zones means that which areas that it can protect, like generator, transformer, transmission line, then substation, right, buses. There are a lot of different zones in the network. So as an example here, if you look at, see, the relays, you define these zones, right? One of the important thing, most of the important thing when you define these sort of zones is that each and every is overlapping. Why this overlapping occurs? Like, why don't you design it, okay, one is just up to here and then the other one is starting from there? Why? Why there is overlap?
Depends on the whole network. You can't just segment parts, or you need to consider everything.
Yeah, like let's say you consider everything, but then generator one, instead of going up to here, I will stop at this point, right? Just at this point. And then I will start the transformer here.
Just in case the generator relay doesn't work, he will now.
Yeah. So nothing is accurate. Like, so that what you do is that it is always adjacent zones are overlapped, right? So if the primary protection fails, then still the secondary protection is there. And the other thing is that boundaries are not accurately defined, right? It's in a protection scheme that you can't show the boundary like 100% here. So it could be here and there, here, right? So that you don't know. So to avoid that or avoid this clarified areas, so then you can introduce these sort of overlappings. And then when you are dealing with the relays, the other thing is that how they communicate with the circuit breakers. Usually you send the trip signals, and then whole this process is, if you look at a manual, then you will find all this information like this, because it is a DC circuit, right? It's working on some sort of activating some points, let's say, right? It's a sort of a DC. That's why that if you go into a substation, have any of you been to a substation? Yeah. So you know that there's a DC part, right? DC batteries and all. So the reason is that all this part works under the sort of DC operation, so that you can see, these sort of relay indications, and then 52T is the circuit breaker indicator, right? And then all these things shows that how that circuit operates. That's all, right? So it's a simple circuitry showing how it works. The next is the characteristics. As I said, we have instantaneous currents and voltage relays. They operate less than 50 milliseconds. Forget about this one. If it is numerical relay, it's the same, right? So probably numerical relays are in the range of 10 milliseconds, like, very, very fast compared to these mechanical ones. So operating time is independent of the current or voltage magnitudes. Once it passes a certain value, then it quickly operates. That's called and then it is not suitable for time grading ones. What is time grading one? As you can see here, when the current magnitude is increasing from left to right, the current magnitude increases, right? And then the operating time reduces. So that is basically time inverse characteristics. You will learn about this time inverse relay when we are looking at the overcurrent relays, right? So it's a very fast operation when the current is high, very slow operation when the current is low. So it is good in a way that more damage occurs when the current is high. So that very fast, very, very high current, it operates very fast. So that's the advantage. And then the relays, there are relays to identify the direction of power flow, right? That's based on the voltage and current magnitude phase angles. You can identify whether the current is going from A to B or B to A. Typical normal overcurrent relay will only look at one direction. That is called directional relays, right? They are not working when the current is going the other direction, right? So that element is called as the directional element, right? Yeah, so this is an extra element. See, when you add extra element, that reduces the dependability of the relay system, right? So they are not, you shouldn't introduce these extra bits if there is no requirement, right? Because once you introduce extra things, then it's the concept of simplicity is reduced as well. Okay, so this is all, and then I will move into the real calculations part with the overcurrent relays now. Okay. This will continue next week as well, but I want to start that because our so you don't want to change your stream, right, from here to English, because you are going to learn now a lot of things there. Overcurrent relays, inverse time, relay burden, blah blah, a lot of terms. You didn't see the cartoon, right? You didn't see the cartoon, right?
Oh, yes.
Yeah, so what we are going to learn in the next part is overcurrent relays, right? Basically how the relay operates when the current is exceeding a certain limit. So the main thing is that we need to understand two terms called fault current and pickup current. Fault current is the current that you don't have any control. You don't know. It depends on the location of the fault, type of fault, whether the fault has impedance, and then whether it is line to line, line to ground, three phase, right? The fault current you don't have any control. But you have a control over something called pickup current. Pickup current is that you set in the relay saying that, give the relay an instruction saying that, okay, the current is above this, do something, right? That is your instruction. So that pickup current is your setting. So if the fault current, typical overcurrent relay is that if the fault current is exceeding the pickup current, the relay will do or send the trip signal to the circuit. Assume that. It's very simple, right? If it is less, then we call it block. The term block means that it doesn't send any signal. Trip means that it sends the signal. Okay. Typical relay, this value is adjustable. Like you can change the pickup value in different ways. In a numerical relay, you just type the value. In a mechanical relay, there's a sort of a plug that you can take it and then plug it, right? I have one in my office. I usually when I come to this class, comes very early in the morning. Probably I will bring it to the tutorial card next time, just for you guys to look at it, right? So the traditional ones, you don't have to this is just to give you some understanding about how the operation and then how these parameters develop, right? Nothing else, right? So that you don't have to understand its operation mechanisms and principles in very detail, because they are phasing out, right? Probably in next, I don't know, like still probably there are substations, you know, with these relays, but could be very handful of, probably one or two in Australia, probably. I don't know, right? I haven't seen, but when I talk to industry, oh yeah, we all, you know, sometimes we have one or two, something like that. So the concept is that what it does is that it creates, you know, it has a disc here, spindle, in a disc and a spindle here. So the disc rotates based on the magnetic fields produced by these two cores, right? Two cores, and then the disc rotating. And then the torque on the disc depends on these current magnitudes. See, flux produced by this one and the flux produced by this one, which means the current actually, because that flux is produced by this current, right? So the magnitude of the current, based on that, the torque on the disc is going to change. So what you do is that, okay, now I set the spring constant or whatever the anti-torque on the disc in a way that, okay, it will not rotate until the current is exceeding certain limit. So that until that certain limit that we define, the torque is not sufficient to rotate it. Once it comes to that limit, the disc starts to rotate. So that's the simple mechanism. And then in these sort of, why do you need this sort of braking magnet? Because once there's a torque, it starts to rotate very fast. So what it does is that using the braking magnet, when this rotates, then it will produce some sort of a anti-torque. Using that, the magnetic field appears here, right? And then tries to reduce the speed of the disc, nothing else, right? So, but in a numerical relay, you don't have any of those things. You just set the magnitude and then it does the calculations, right? So, what it does basically, it has AC signal, produce magnetic field, torque, and then rotation of disc. That's all. And then, if we can control the travel time, then we can say that, then you can initiate some sort of change the operating time, because that is the travel time, right? So that's called, is done by spiral looping and backstop. Like as an example, you can change the stop posture. Disc can rotate 90 degrees or 45 degrees depending on the location that you stop it, right? And then how do we control the pickup? Change the number of coils, right? So if you change the number of coils, like increase the number of coils means it will start to rotate for a lower current. Reduce the number of turns means that you need higher current. So very simple, right? So usually these relays that you can modify them to have some sort of an inverse time characteristics. So that is the one that we need to learn, and then we need to look at those characteristics and then how the different standards define them. We need to look at those things, right? So what is it's called IDMT relays because inverse definite, pardon?
Inverse definite
Yeah, definite minimum time character. Why definite minimum? I will explain it. Right? So, if you look at the characteristics, it's like that. Okay? So, what happens is that with increasing the current, right, we will look at what are these, multiplier or whatever, right? Those are the standard terms that we use, right? But for the time being, think that, okay, the fault current is increasing. And then when the current is increasing, the time reduces. But you can see that the time reduces to a certain level. After that, like let's say, that is the minimum time that the relay needs. Because this is like, you can't bring it to 0, right? It comes to 10 milliseconds, let's say. So that after that, whenever you increase the current, still it's the minimum. So that there is a definite minimum time there. So that's why that we call it as inverse definite minimum time relay. Right? So the characteristics here is that operating time is inversely proportional to the fault current magnitude. Right? And when you plot these sort of figures, one of the issues is that, say, if you can change the pickup current of a relay, then these characteristics can be changed. Therefore, I don't want to have multiple characteristics given for the same relay. So what they do, they look at this x-axis in different way. Instead of fault current, they divide the fault current by the pickup current. So, if you set the pickup current to 1 amps, then if your fault current is 10 amps, then the value is 10. If your pickup current is 2, and then now your fault current is 20, then still it is the same point. Got it? So that you can, this is a normalized graph. So that instead of looking at the fault currents, we are looking at fault current divided by the pickup current. So that you don't have to have multiple graphs there. So when you are looking at these relays, yeah? No? Okay. When you have these relays, couple of specific parameters that you need to look at. One is called current setting. Current setting means that what is the pickup current? That is called as current setting. We call it as old days plug setting. If you look at the old relays, we call it as plug setting. Why plug setting? Because actually there is a plug to, I will show you in the mechanical relay, there is a plug that you can check and push in, right? But now miracle relay, you don't have the plug, so it's called current setting. So it is usually in 50% to 200% of the rated current in step of 25%. So usually the relays are, these relays are, there are two types of relays. One works in 5 amps, the other one is 1 amp. Right? Some numerical relays, you need only 1 amp in there for their like normal operation. So that all these calculations, 50%, 120%, it comes based on that value, right? If it is 1 amp 1, 50% is 0.5. If it is 50 amp 1, 50% means 2.5, right? So one of the important thing is that where it starts, the initial pickup value. Standards defined. So you can't just, let's say, if you define rated as 1, right? you usually can't operate the relay just above the 1. It's not going to work. You need to have some sort of a gap there, right? You can't define 1 there, right? It can be, then what happens is that it could operate at 0.95 as well. Therefore, usually they define it in the standards, according to this BS, this one, 1.05 to 1.3 times the rated, right? So usually in that range, that if you look at the characteristics here, this can't be 1. This will be something around 1.05 to 1.3, because when it is close to 1 or below that, the operating time should be 0 or infinite. Otherwise the relay will operate during the loading conditions, right? I will stop after this one. The other one is called time settings. Time settings means that adjust the, let's say, if it is, think about that disk, angular travel, like let's say, whether it has to run for 90 degrees or 45 degrees. Easier to explain with this. That's why, right? Easier to explain is rotation of the disks. Like it's whether it is rotating 180 degrees, 90 degrees, or 45 degrees, will give you the time difference. So that for the same current magnitude, you will have different operating times. So if you look at this, that's why that we have this sort of set of curves. See? So for the same time, multiples of, let's say, tap value currents, let's say this is the fault current divided by the pickup or current setting. If it is 6, you have multiple of operating times here, see? Because this is called the current setting or time setting of half, time setting of 1, 2, 3, 4, 5, 6, like that. So what it does by time setting, it changes the rotation of the disk, like let's say the travel distance of the disk. If you reduce the travel distance, operating time will be high or low. If you reduce the travel distance, time will be lower. So that, see here, time will be lower, which means that half means travel distance is half. Put it in that way. Full, this one. If you make it 2, further longer. So that's how that you define these characteristics. We'll go from there. Our tutorial is based on these relays, right? But I will do one example before the tutorial. Okay.
So you get a percentage for dependability.
Yeah.
You get a percentage for security.
Yeah.
How does that equal percentage for reliability?
Or see, the reliability comes with, say, when you are calculating the reliability, it is, let's say, you are looking at, how can I explain it? Security and dependability as, wait, hold on, dependability plus security and, okay, it's like this. You suddenly forgot it. I think it's the average of these two, as I could remember.
Yeah.
But I will double check.
Okay,
Okay,
yeah.
because that's what I can remember.
Yeah.
But I will double check and then.
Yeah, I
let
mean,
you know.
average of the two makes sense.
Yes, but then I'm
Yes.
not 100% sure.
Yes, okay.
Okay,
Okay,
I'll look at it. Thanks for
thank
that
you very
question.